Well, I'm very grateful to be able to explain this story once again. I mean, well, twice, I guess, because I wrote a book about it, and I've already given one presentation. But it's a story that I thought hadn't been told, and I was surprised to know that this had gone unnoticed, because most of what I'm going to tell you today was written or recorded in a journal, an unpublished journal, until 2008, when Ashby's family decided to introduce it into the public domain. So they created this archive with all these notebooks or journals and other manuscripts that no one knew about except for the close people to Roger Ashby. And that's how I knew about it. Now I will tell you how it relates to my research. Of course, I wasn't an expert in cybernetics, though I had learned, or I had done some work related to my PhD to the VSM, the Viable System Model, Stanford Beer. And that's how I came into contact with cybernetics, but without any background regarding cybernetics. So I didn't start with the classic works with Wiener or Ashby himself, but basically trying to understand how we could apply cybernetics to organizations, because that was what my PhD was about. At the time, I wanted to use that system methodology and combine it with others, which I was trying to develop at the time. And I noticed something quite fundamental, because somehow I had an idea that human systems differ somehow from cybernetic systems, though it's something that we don't really question. We somehow assume that social systems are cybernetic systems, and they are to some extent. But I was trying to figure out whether there was a theory which applied to the human world, which somehow was compatible with cybernetics, but something different. And that's how I realized, or I had an intuition at the time, that cybernetics was addressing one of the layers. Well, I say layer to call it somehow, but I would say between the different groups of sciences, there's a layer in between biology and the human sciences. And for me, cybernetics seemed to fit, what I knew about cybernetics at the time seemed to fit in that intermediate layer between biology and the human sciences. I say it seemed to fit because at the time it was just an intuition, and I thought that the theory of viability of Stanford Beer basically was providing that theory. But of course, there's a lot of the human world in that theory, so you can't say, well, this is only about the animal world, or it's only to some point, and even himself, he links it to orthopoiesis. Well, I don't think it's the consensus now in biology, orthopoiesis, but somehow he saw it grounded in biology. Okay, well, a few years later, when I finished my PhD, I went deeper into the question, in the sense that I tried to provide what was the actual foundation of science. And as I understood that at the time, I thought that behind the system methodologies, there was a general theory, or there had to be a general theory, scientific theory, and that general theory had to be grounded on what I thought at the time world hypothesis. Though I had a very vague idea of what a world hypothesis, I developed to some extent what I meant. But basically, in my first book, I do develop that world hypothesis, and as I understand it, that a world hypothesis is something that provides a ground of science, and not only science as understood like a general systems theory, in which we are trying to find a very fundamental science, nearly a theory of everything, or a very abstract or mathematical theory. No, it's not that in that sense, but more like a theory that grounds the different domains of science, and each of them is independent in the sense that there's some laws that apply to that level, but not independent from the level somehow which it springs from or it's grounded on, because the biological world, as we know, is grounded on physics. but at the same time, we can't reduce biology to physics. And the same goes for cybernetics, as I understand it, can be reduced to biology because it's something different, though it doesn't contradict, as I see it, the laws of biology, on the contrary. And I think this is what somehow Ashby struggled with, because he knew that he couldn't contradict biology, but at the same time, he was at something which was different from biology, and he himself was after an even more general theory which could explain the biological world, but and he even ended up talking about the theory of machines, which were even more general, more abstract. But before that happened, and he developed that theory, which we can find in the introduction, he had been working very early on the problem, which is what I think unites or should be the fundamental question behind the domain which I'm trying to explain, and I think that his theory basically is unifying this domain, and this domain is basically constituted by three sciences, one of which is physiology, the other especially neurophysiology, the other is psychology, and I will explain what I understand by psychology at this point, because psychology has also outgrown and is being now very, very much absorbed by cognitive science, and we talk about cognitive psychology, so it's not really that the psychology I have in mind, but the one that was up until the early 20s or even the 30s was the consensus, and then it lost ground, and I think as from the 50s, the psychology that we now understand by psychology is not the actual psychology I have in mind. Okay, and then there's ethology, which is the behavior of animals. So I think that Ashby was quite versed in all those domains, and he proves himself by his background that he was very familiar with that. And he came in contact also with ethology towards the end, when I think he basically found how to complete the theory he was working on. So this theory, so to speak, starts, I will go to it, in the late 30s, though he starts to have some hints, some ideas previously to that. And the 1939 is the year that I think that this history that I'm trying to explain today starts. In fact, in December, but that history ends just before he comes or he formulates the law of recursive variety. So this conversation won't, or I mean, in this presentation, sorry, I won't address the law of recursive variety. I think Stuart will tell us more about it. I'm going to stop just before, because that's when I consider that the theory was complete. So I don't want to disregard what came later, in the sense that it may be important, but what I was looking for, a general theory to unify a domain, I couldn't find it later. So I stopped there because I saw what I needed. It's like in biology that we have the theory of evolution that has managed to unify genetics, but also the different domains of biology, and that was after the two fundamental contributions of Manel and Darwin, and we saw like a biological synthesis or the evolutionary synthesis. Well, I'm kind of seeing something the same, though it didn't go public, and this journal only saw the light in 2008. So I'm trying to argue that something similar to what happened in biology, which was a unification of biology in the late 30s and 40s, in roughly 12 years, it took place. It happened gradually, but it was somehow something he worked alone. And when he went public with his theories, which was not only in design, but also in an introduction, at the beginning, he had developed somehow, but I think towards the introduction, especially when he published it, I think he somehow went another direction. So I don't know whether it's a good direction or not, but I have some issues related somehow with the constitution of the cybernetic world. So now I'm going to explain briefly, before I enter, that I understand the cybernetic world as constituted by 2 dimensions, which, like all the different domains of reality, have different dimensions of space and time. This is, of course, assuming my world hypothesis. But in the case, I won't go into the other worlds, in the case of the physical, the biological, but I do want to stress that the cybernetic world somehow has a dimension of time and a dimension of space, which is different from the other worlds. So what is the difference? The difference is that when we are talking about the cybernetic world in terms of space, we have a duality which is very common, and we somehow take it for granted, especially, as I said, in those different sub-sciences that constitute this domain, which is the central periphery. When we talk about central, we understand an organism and a central nervous system. And when I talk about periphery, we understand the receptors and effectors, somehow the elements that somehow are aware of the environment. Well, that's something as simple as assuming that the organism is not separate from the environment, and that the periphery equals the environment and the central equals the organism. Okay, so that's an assumption that I make, that I think it's present in all those fields, and I think that's what somehow was behind the development of the theory of Ashby, and he took for granted that you can't really separate the organism from the environment. What I call that spatial duality, the central periphery. And in addition, in terms of time, you have a different duality in the cybernetic world. And that duality is past, present. When I say past, present, I say that those 2 dimensions are simultaneous, in the sense that normally what prevails in the cybernetic world, in the world that I'm going to introduce, is always the behavior that has been successful. So that
excuse me for a second. Are you scrolling down your slides, or?
No. I'm just doing the introduction.
On the first page, right?
Yeah. I'm still on the first page. Sorry.
Okay.
I just wanted to provide a bit of context.
Oh, okay.
Yes, but I will do them quite fast. But I thought without the context, it won't be helpful. Mm-hmm. So basically, in terms of space, I think that in the cybernetic world, what we see is that unlike the biological world, in which we have a history of somehow evolutionary success somehow, and that's basically the past that starts with an origin. In the case of the cybernetic world, what we have is that what is learned during the life of an organism is always an accumulation of successful trials, and those are the ones that are established. So when I talk about trials, it's the last success which is kept. And that's why the concept of time is different in the case of the biological world from the cybernetic world. Well, those 2 things, those 2 dualities, are implicit in the development of this theory that I'm going to introduce. I have chosen this slide because I thought it's quite interesting, because when Ashby ponders about his contribution and his major contribution, he's very humble in the sense that he thinks that he's made a huge contribution, but whenever he has been asked to talk about things, he's maybe never stressed it enough. And he thinks, as you can see in this slide, that he should be more assertive. But he's never wanted to be famous or to show that he's somehow a great person. So he somehow hasn't done enough to promote or to associate Ashby and the theory of ultrastability. Well, the theory of ultrastability is what he had developed in design and what he thought was his major contribution. Okay, and he thought of himself of someone that was just interested in the problem of the brain. He had solved it. Now he wasn't interested anymore in that problem. And even though there was other problems related with that, the main problem was already solved. So there was no point on him to stress on that, and that's why maybe he had to move onto other things. But I think his contribution was even something he wasn't really aware of, to the extent he can make such a big contribution, even if he uses the words major discovery, because at this time I think he had in mind some variations to his original discovery. Okay, we are talking about 1956. He had already published design. He had, I think he was, if not, this is the year that he published the introduction. And something went in between, which is what I take to be his major contribution. Okay, so this is the context. So what happened in between, or when did all this start? Well, I said that there's this archive where you can find all these journals, or all these volumes of these journals. It's a huge amount of pages, more than 7,400 pages in 25 volumes. Of course, it's impossible to summarize all that. And he kept up journal since 1928 until the end, in 1972. And from there, that would be the quarry from which he would draw a lot of, I mean, he would elaborate a lot, and he would do some manuscripts that never saw the light, but other things which we have, his papers and his two major books, came from there. But there's other things that are also interesting to look at, and I think it's when he's changing and evolving that theory when we see those insights. Okay. Well, in 1939, as I mentioned, is when I consider to be the beginning of new cybernetics, because he somehow looks at what he has done before that, and he doesn't think that there's anything strong enough or that he can use to build and to develop his theory. So that's when he decides to make a fresh start. And that fresh start is with the question of stable equilibrium. And that's the foundational idea. Because as I will show later, stable equilibrium is related to adaptation. And he makes the link in that seminal paper of 1940, okay? There's another unpublished memoir, The Origin of Adaptation, which we also see the ground of ultrastability. And we see the theory that's called break theory. And I will mention it briefly, but basically what the idea behind all this is that we have an organism that is trying to adapt to an environment and somehow breaks, in the sense that changes organization until it reaches an equilibrium in which the variables, when I say variables, what he calls essential variables, are within limits, and this is connected to homeostasis. Okay. At that point, he's looking too much at the organism, and he's not introducing the environment enough, and only to the point that somehow it's helpful in the sense that the organism has to move to be in adjusting to the environment. But it's a matter of adjusting. So somehow the organism is not so much part of the system. The environment is not so part of the system. Okay, and this theory, which takes 15 years to complete, is, as I say, completed on the 12th of February of 1956, okay, in the 7th volume, just before he formulated the law of recursive variety. Okay, so now we can start. That was the context. I said, well, you said 7 slides, so I had to make sure I got my point across.
Well, it's...
Oh, okay, so all the I would say that the big questions in science are always questions that unite different disciplines or different fields. Okay, in this case, the question that I think is behind neo-cybernetics, as I understand it, which is the unification of psychology, ethology, and physiology, is to explain something that is taken for granted. I mean, when we look at the animal world, we assume that it's in equilibrium with its environment, and that's something somehow we always assume it. We talk about ecosystem in equilibrium, and something is wrong when it's not in equilibrium. But if everything is okay, everything should be in equilibrium, and it's normally an intervention from outside us, for instance, humans, that destabilizes those systems that somehow should be in equilibrium. So that is something axiomatic, and it's something that is intrinsic to the cybernetic world, but that's the actual question, the scientific question that has to be answered. So how come the cybernetic system maintain a stable equilibrium? When I say cybernetic system, I'm assuming that we have an organism with its environment, and that organism with its environment is in equilibrium. Because normally we always think in an organism with its environment as something it has to adjust to. So it's like in something that's not part of the system. So here, when I say a system, I mean the organism or the animal and its environment together. So how come they are in a stable equilibrium? Well, that question of stable equilibrium is the question of adaptive behavior. So if we answer that question, we will have a theory of adaptive behavior, because a cybernetic that is in stable equilibrium, it means that it's adapting, that it's doing well, that it's somehow better in terms of the adaptation that it's learning. If it's not in a stable equilibrium, somehow it's not adaptive, that system. So we can't separate really the question of stable equilibrium from the question of adaptive behavior. Because basically the foundational idea that he sometimes argues in that seminal paper is that it's necessary for the existence of any cybernetic system to be in stable equilibrium. So somehow one assumes the other. You can't really, they are intrinsically connected. Okay. But that's not enough to have that foundational idea. He will have to build on that, and he will have to prove his point, and that's what he tries to do. Okay, so the first period starts with that intuition, in the sense that adaptation is related to stable equilibrium, or stable equilibrium is the same as adaptation, and he will come. He will talk about this idea of feedback, which we are already familiar with in cybernetics. And he will say that for a system to be in stable equilibrium, then there has to be a circuit that connects the environment and the organism, and that's somehow this feedback. And he will say that it's two ways: the way from the environment to the organism, and then the organism also affects the environment. So there's that two-way circuit. But he's clear that the organism and its environment are functionally related, and this is a fundamental idea. I mean, it was already assumed in that duality that I said, the central and periphery, or the central nervous system and its environment. They are functionally related, but somehow here he's explicitating this idea. The problem is that at this point, this feedback is explained in terms of homeostasis. So he basically saw that those variables that are off limits, and they should return to the point where it's in stable equilibrium. Basically, they are a reaction that takes place by creating an imbalance that has to be reached again. So basically, he was thinking in homeostasis in terms of balancing. Okay, so like contrasting forces, in the sense that if something moves one way, I have to counteract it until I reach that stable equilibrium again. So that's how he understood feedback at that point. It has to, when the variable is changed, it has to have a mechanism that balances again and reaches that level of being within limits. Okay, well, in the origin of adaptation, he will go one step further, because somehow stable equilibrium and homeostasis are parallel processes. So he will understand that in the case of, for instance, a child approaching a fire that can burn him, he will see that the organism there is going through changes internally, okay, in adjusting to the environment, and somehow when he finds that adjustment, in parallel, those variables are stable. So somehow he sees that stable equilibrium between the organism and the environment, which coincides with the homeostasis. So he will think that somehow there's a parallelism, a correlation between homeostasis and stable equilibrium. Something that happens inside and something that happens between the organism and the environment. Okay, At that point, he's thinking in life-threatening situations, but then he will have to wrestle with the when it's a signal, when it's an impending threat or something to the organism, which it's not like a fire that I'm going to be burned, but it's like a predator that's coming to me and I have to run. Okay, so that's something he will have to deal with later. But at this point, he thought, well, I have to isolate the problem. I will see when there's a real danger, actual danger, a hard fact that is life-threatening. And if I understand that, then I can move on to understand the other. So at that point, he developed what is a break theory, in the sense that when that equilibrium is not reached, or has to be reached, there's a process of breaking. When he says breaking, he means an internal change of organizations until the actual brain and the environment reach a stable equilibrium in which the variables are in range. The variables are, I mean, temperature, blood pressure, I don't know, anything related with the interior of the organism which is necessary for survival. Okay, and that's how he understood it at that point. Okay, in the second period, he goes one step further and he understands that you have to understand the system as something relatively isolated. So you have an animal and environment. Here, the animal and environment are getting closer, but somehow they are isolating themselves from the rest of the world. He's saying properly isolated, then he of course says that you can't isolate it completely, so somehow he has to assume that as a working hypothesis, but he doesn't really think that it's absolutely separated, since there's an environment there, but somehow he's trying to minimize it to be able to explain and to develop the theory. So it's more like a working hypothesis. Then he will have to give up that because it's somehow not helping him develop the theory. What at that point he also realizes that he also has to, if he wants to understand the problem better, he has to leave aside what are inborn fixed reflexes, and he has to concentrate on learning. And basically he starts understanding that all those inborn reflexes are more explained by natural selection, and they are adaptive in the sense that evolution has come to them, or through the process of natural selection we've come to develop them, but somehow those are different from neuronic adaptation. When I say neuronic, what I mean is they are related with the brain, and the adaptation that somehow develop through the life of an organism, and those are the ones that somehow are different from the ones that natural selection has already instilled in us through the history of the species. So somehow he sees that there are different ones. One is related with something fixed, and the other is related with something learned. Okay, there are two different kinds of reactions, as he calls them at that time. And the problem is that now he sees that homeostasis and stable equilibrium need to be understood also within neuronic adaptation. So it's like a more general theory for him, which includes homeostasis and stable equilibrium, and somehow he tries to combine both in this neuronic adaptation, but he sees that there's something here that is missing, and he can't make sense of how to combine those two. Okay, in design he will make a step further, in the sense of he will see that adaptation is about fixing or finding or selecting a line of behavior. So similar to the theory of evolution, in which there's something selected which is passed on to another generation. So we will say, okay, so maybe it's about the selection of a line of behavior which will keep these variables within limits. So okay, so he's trying to combine this idea of homeostasis and also this idea of evolution in Darwin terms, though they don't fit quite well together. Okay. Later, he will have to try to disentangle those two things, stable equilibrium and homeostasis. And it will be difficult, but I think this is the transition period in which that takes place, which is the third period. There's a technical term, that transducer with memory. Transducer, basically, it's something that comes from information theory. And he comes near to these ideas at the time when the radio club is held. And he attends the first meeting, and he doesn't know how he's got there because he he's somehow not a junior, and they didn't want professors, and he talks that maybe his young appearance has got him in. But the thing is that he starts to get in contact with some scientists, and especially some British scientists that were trying to implement in the fields the theory of information, and also which was somehow the forerunner of the radio club, some conference that had taken place related with ethology. So that also means that there was lots of people related to zoology at that time, biology, in addition to what we found in the US, in terms of the cybernetician had a background in mathematics, in engineering. But here, I would say that they are more related with biology or with zoology, or more predominant, even though there's also the balance with engineering and with mathematics. Okay, but that's something I would say that added to that heterogeneity of influences, which were useful for Ashby. Okay, so this is a crucial moment in which he sees that he can cast the stimulus-response framework, which we know comes from psychology, in terms of information. When I say information, I mean input and output. So he starts to see, okay, he comes into contact with certain machines, and he says, okay, most of the design of this machine have an input, an output, and something in between, which is the storage, the memory. And he starts to see, well, this is useful to think about it in these terms. And well, maybe, I don't know whether he was aware or not, but he somehow united two worlds which are separate in psychology in terms of the perceptual world, when we think of gestalts, and when we think about behavioralism, we say, oh no, I only look at behavior. But somehow with the input-output scheme, you can combine both. And somehow the input and the output, one is the inverse of the other. So somehow they are not separated worlds in which one is related with what the eye sees and the other what the legs do, but somehow you can combine both. And this is a very important moment, because he can also bring together the organism and the environment, while before he had given too much emphasis to the organism. Okay, and this is the crucial moment in the last period. He sees that what I said before, that the noiseless transducer, which is a term that comes from information theory, and basically he sees that the absolute system is conserving information. So he says, okay, so if it's a noiseless transducer, there's a transformation of an input to an output, and somehow there's no new information there. It's always the same information, which is conserved within the system, and somehow the transducer is not adding information. So the information is kept there, and then he asked himself, okay, so this is information which is conserved, but somehow it has entered. Before it became somehow part of the system, it had come from somewhere else. And that somewhere else is he realized a second environment. And the second environment is that input, which is like a disturbance that comes from outside and makes it inside. But makes it inside in the sense that when the organism fixes that new information inside, is when it's learned to behave differently. So when we are talking about memory, it's very important to understand that what he has in mind is a different way of behaving. So, and what is accumulated within the organism, okay, are different ways of behaving that have resulted in better adaptations. So when he makes the crucial move is when he tries to understand, so how does this new information or extra information, if we understand that the system has already an environment and an organism, how this second environment and the information from this second environment enters? Because that's crucial, because that's what will explain adaptation. Okay, so the answer, and this is the answer to that question of why cybernetics maintain extra equilibrium, is because that information from outside, from the second environment, enters, okay, by way of or through the feedback mechanism, and that's destroying behaviors which were not useful or not adaptive, and replacing them with the ones that are useful to adapt to. And that's somehow one is destroying the other, or one is replacing the other. So that's why we can say this adaptation by information destruction. So that's a very important. I mean, before I remember that the first presentation that I did, and in the book I talk about information forgetting, but it's not so much as forgetting as replacing or as destroying. So you need new information to destroy the old information, because somehow you're changing one way of behaving by replacing another. This is very important, okay? Because that's somehow the stock of behaviors that are more adaptive are the ones that somehow have proven by trial and error that they were better. And somehow, in order to enter the system, they had to destroy something. Otherwise, they wouldn't enter. And this also is compatible with the idea of the noiseless transducer, in which there's a conservation of energy. So somehow there's some energy inside which is preserved, and unless you want to introduce new information, unless you destroy some information from inside, you can't introduce information from outside. Okay, and that's, for me, is the general mechanism that would explain how the cybernetic world works. Okay, here I've chosen a sentence which he uses before he comes to this formulation or to this understanding, that in which he had already the idea, and he writes, all improvement is performance. In performance is obtained solely by the extraction of the less good, and this is crucial. I mean, unless the organism is able to destroy certain behaviors by incorporating new behaviors, so replacing one with the other, it's not going to be more adaptable to the environment. So somehow this is the theory, or the general theory of cybernetic systems, that explains adaptive behavior. And this is my last slide. Sorry, I don't know whether I took too much time, but I think I had to provide the context before I explain the theory.
That's okay. Can you say a little bit more about how do you destroy information? I mean, you cut them into pieces, or just delete them, or forget, or, I mean, how do you actually do it? Exactly.
Well, you have to think about the absolute system, the organism or the animal and its environment, as a system together. Okay, so you can say, oh, well, where is the information? It's within the two. You can't say, no, it's in the brain. No, it's in this part or that part. No. It's within the two together. And the feedback is the means by which it is destroyed. So when the feedback reports success, or trial that has been successful, somehow that is letting the extra information from outside the second environment in. So that's how it's destroyed, basically by the feedback, through the feedback mechanism.
Cancel it.
Well, replaced, I would say.
Replace.
Yes.
Okay.
It's destroyed by hitting one with the other, or getting one in by the other coming out.
Okay.
And that's true feedback.
Can we play a
But we always tend to think about feedback, about something that at the end of the day comes down to the organism, no? That it's reported to the organism. But in this case, the feedback connects the two. So you can't say, no, it's here or it's there. Otherwise, you wouldn't have a second environment. You would still have one environment.
Do you have more questions, or do you want to listen to Stuart?
If I could just make one point, because your distinctions are very clear. But I think the element of destroying and replacing is only an element. What we're talking about is the transformation of the assembly between those separations of self and environment. And transformation is almost like an alchemy, where you're creating a new level of complexity. And if you're looking at evolution, it is the evolution of complexity, not just replacing, substitution, thinking of them as things, but thinking of them as realigning the assembly of relationships into new organisms that have different levels of complexity to deal with the complexity of the external world.
Exactly, that's a good point. I think the best way to put it, since memory is related with behavior, it's a change of behavior.
If I could interject here, I would say that you painted the conundrum of meaning, which I think in the world in which it actually doesn't exist. The problem is I see what you're saying, which I think is very clear, and I agree with Lowell that your distinctions are clear, but there are two different sources of homeostasis. One, a sense of homeostasis in the natural world in which all human beings exist, and a second, an internal homeostasis, which is the one in which we experience in our general biological system of being going from germ cell to germ cell. This internal homeostasis has a different set of parameters and variables than the external homeostasis, which has its own set of physical variables. So that I don't see the conundrum in which you're painting here in the same light as you do. The mathematics of both of these systems are rather different from each other. And this is where I wonder what Ashby's mathematics is all about, because they are, from a modern molecular biological perspective, these two forms of homeostasis use different variables, different mathematics, different descriptions of reality.
If I could just add the fact that Rosen developed the ideas of a model, the external model and the internal model. But what we're talking about with humans as a dual system, we have models in the physiological side of levels of homeostasis, and then we have the higher level of the organization that he creates, he, she, it creates. So you have a dual level of models. And what I think Jerry is saying is they have a different logic and different mathematics, and we can't just assume one into the other.
I have one more question for detail. When Ashby talked about stability or stable equilibrium, I think from my reading of his stuff, whether or not a system has stability can be well clearly established, yes or no issue. But did he ever discuss about how stable, I mean, the extent of stability?
Yes.
Is there a measurement of it? I mean, like if you compare a bird, a hummingbird with a turtles, and the hummingbird life is very fragile, and the life of the turtles is kind of much more stable than that. So what kind of measurement he Ashby tried to use, or any work on that?
Well, I would say that stable equilibrium for him was an axiom. So he would say that stable equilibrium is all over. So there's no degrees. I mean, it's either there or not. And if it's there, it's existing, it's surviving. And if it's not there, it has a problem. So basically, he would say that it's the exception. So to find something that is not in stable equilibrium, it's really difficult. Because if it's existing, it's either in stable equilibrium or it's not. And if it's not, then he would say that he doesn't need to explain it.
So he didn't discuss the degree.
Yeah, he does. He talks about stable equilibrium at the beginning. He said, well, the stable equilibrium has to be in all the parts. So he would say, okay, so if you look at the neural system or the nervous system, he would say, oh, each neuron has an environment. So there's a little environment for each group of neurons. And then you have the whole brain with its environment. So he would say that it is assumed that all the parts are in stable equilibrium for the organism to be in equilibrium with its environment, okay? But then he will say, no. When he moves on, he will say, no, the property has to be of the distributed system. So it can't be just in the parts. It has to be the whole, because otherwise we are reducing one equilibrium to the other. And he would say, no. I have to assume that the whole thing is in equilibrium, and I can't really say that the equilibrium is in the parts and therefore it's in the whole. It's in the whole. He will say it's a property of the whole.
Okay, then one more example. In the case of fighting, like the capacity of a fighter, like we regular people versus James Bond or Die Hard. I mean, there's a difference there, right? Some of our average person's stable equilibrium of his life it can be destroyed at this amount of the force. But for James Bond or for the die-hard guys, the Marines, special forces, they seem to be much more stable than regular us. So that kind of a difference, I was wondering if we had ever discussed.
I would say maybe this clarifies it, but when we are talking about stable equilibrium, we are assuming, or it's implicit, a functional relation between the organism and the environment. So if there's a functional relationship, which there is in the cybernetic world, it's in stable equilibrium by necessity.
But you can measure it using Markov chain models, Jason.
Markov chain model.
Markov chain models.
Yes.
And also Lyapunov function also used an analogy of how deep how deep that little stuff is.
The other thing is that you would have to measure the whole life of an organism, because maybe
So
if it's changing.
You can do it in simulations.
Yes.
Peter wants to say something.
Statistically, you could be able to come with a figure.
I mean, I agree that
as I understand what you're saying, then the notion of stable equilibrium is, if you would, the very ultimate notion of the functional existence of systems, and that the individual components of the system are not necessarily either conserved or otherwise.
No,
they may
not
be
exactly.
created and
I would say
destroyed
that's
at will without respect to their own identity.
Well,
so
I wouldn't put it that way, because at the time when he was talking about the parts in stable equilibrium and the whole system, he was thinking about machines. So he was thinking that there's different elements in a machine that has to be in stable equilibrium. So he was basically seeing that the different, so to speak, parts of the machine are in stable equilibrium. So he wasn't thinking so much. Of course, he had to relate it to the nervous system, and that's when he came with this idea of the neurons with a little environment. But he would say he would eventually give up that line of thought, and he would say that it's the distributed system or the absolute system which is in stable equilibrium.
Why is it so important? Can you explain that? Why is it so important?
Because it's something axiomatic that has to be explained scientifically.
I mean, is there follow-up research? Is there current research? Or is this just history?
Well, I mean, this is a general theory in the making.
Is anybody working with that theory?
Well, it's not known.
You don't maintain your physiological variables within the operating limits. Organism dies, and similarly, if your behavior in a social context goes off the rails, you cease to be able to function in a social context. There's an operational, an operational definition of stability would be how long does a given arrangement persist and successfully maintain the system within its operating limits. So the length of time that a system persists gives you a measure of its stability vis-a-vis that environment. And
I understand that.
In the homeostat, there were sequential circuits that were constantly being tested, and they would go and regulate for some period of time, and then when when the system went outside of those bounds, the uniselector would find another one and then another one. But the relative stability of each one of those circuits, or its ability to control its a given environment, is the length of time that it is able to do so.
But in the meantime, we have moved to steady state instead of equilibrium, and all kinds of new developments have come up. Why is this still important?
Bernard here, may I comment, please? Around the time that Ashby was writing Design and Introduction to Cybernetics, a literature or a research interest began on self-organizing systems, which Ashby contributed to. And the main insight here is that self-organizing systems have internal to the system variety generation. So new stuff is arising inside the system all the time. You know, we are self-organized systems like that. We're always having new thoughts, which we question and so on. And this is learning, where learning becomes a selection between the new behaviors or the new concepts that we are evolving. We select the ones which are considered successful in the sense that they are coherent with our existing thinking and behaviors, and also produce effective results with respect to the problem solving we are engaged in the environment. Now, I've put notes in the chat which show there's a long literature, mainly through Pascal and his theories of learning, which draw on Ashby and von Foerster's concepts of self-organizing systems, including simulations of the dynamics of learning, which has a kind of energy conservation economy inside the simulation. I myself constructed such a simulation for acquiring the skill of keyboard skills, keyboard skills, which I finally got around to publishing, I think about 6 years ago, 7 years ago. So I consider the work still, these concepts still to be current. The only parallel I could find in recent literature are John Holland's concepts of what he calls strong adaptation, where again he uses models, as in genetic algorithms, he's the inventor of those, in which there is an internal to the system generation of variety, akin to meiosis in cell reproduction, in which new operators or new structures are produced and then tested out against the environment. Okay.
But you can, of course, you can see all kinds of parallels between those metaphors of John Holland and this, but I don't immediately get what you get from this.
Well, in the case of the work of Pascal and colleagues and John Holland, the work includes computer simulations, models of what they're trying to explain. It's trying to explain how new behaviors arise, how learning occurs.
Okay.
There is internal to the system variety generation.
We still have 2 more presentations. Let's hear Stuart. Stuart.
Yes, okay. Can you hear me?
Yeah.
Okay, well, this has been a fascinating discussion, and thanks very much to Manel for his study. Where are these books by Ashby available? Is there only one copy in a library someplace, or are they published?
Sorry?
Where are these notebooks from Ashby available? Is there only one?
There's a web page. If you go to the W. Ross Ashby archive, it's a web page available. I don't know whether I can send you the link. Wait.
Yeah, in the notes, I've given a link to a particular paper in that archive.